Today we are going to study Werner coordination theory. Werner coordination theory, which was proposed by Alfred Werner in proposed by Alfred Werner in 1893. Okay, so before this theory, chemists could not clearly explain the structure of coordination compound. Even when compounds had the same formula, they behave differently and that created confusion. For example, here. Here, cobalt and Cl3, 6NH3. This color is yellow. Now, here cobalt, Cl3, 5NH3, and here the color is purple color. And now here cobalt, Cl3, 4NH3. Here the color is green and sometime violet color. So here the metals, the ligands, all are same only, same types of ligand, same types of metal in all compounds, but why they are showing a different color? This created very confusion. So Warner gave a very simple and powerful idea. A metal ion shows two types of valency. A metal ions shows two type of valency. One is primary valency, another is secondary valency. Let's understand them one by one. What is primary valency and what is the secondary valency? Primary valency is equal to the oxidation state. Primary valency is equal to, numerically equal to, oxidation state of the metal, equal to oxidation state of metal. It is ionizable. It is ionizable. Meaning what? Meaning it can break and exist freely in solution. Meaning it can break and exist freely in solution. It is usually satisfied by an ion. It is usually satisfied by anions. This is the part of compounds that can separate in water. In simple term, this is the part of compounds that can separate in water. Okay. So this is about primary valency, and what is the secondary valency? See once. Secondary valency is numerically equal to the coordination number. equal to coordination number. It is non-ionizable. It is non-ionizable, and it is satisfied by ligands. It is satisfied by ligands like NH3, H2O, etc. It remains attached to the metal ions. It remains attached to the metal ion. In simple terms, these are the groups that stay directly bonded to the metal. These are the groups that directly bonded to the metal, to the metal. We'll discuss clearly with an example. Let's take an example: cobalt NH3 whole 6 Cl3. This is a coordination compound, and now analyze it. Here, 3 chlorine are outside. If you break this compound in a solution, okay, in a solvent, then cobalt NH3 whole 6, that is minus plus 3 plus, you will get 3Cl minus. So this compound breaks in solution into two parts. One part is complex part and another part is ions part. So here total number of ions is total ions is 4. 3 chlorine ions are outside. They satisfy primary valency. They satisfy primary valency, and 6 NH3 that is present inside this coordination sphere. And apart from metal, whatever present inside this coordination sphere known as ligand, and this ligand, these 6 ligands of NH3, they satisfy secondary valency. Satisfy secondary valency. So it releases total number of ions, uh, that is 3 chlorine ions and 1 this complex ion. As this complex ion having a positive charge, that's why this complex is known as cationic complex. Now for example, another compound, that is K4FeCN6. If this compound breaks in solution, then this will give 4K plus and FeCN6 minus 4. So here the complex part is a negative ion, that's why this is known as anionic complex. Okay, that we will discuss later. What is this cationic complex and anionic complex? Okay, now we are discussing Werner theory, right? Now see, Werner also said something very important. Secondary valencies are directional. That means if you draw the structure here, cobalt, NH3, 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 and this NH3, because they are forming coordinate bond. That's why secondary valencies are directional in nature. So secondary valency are directional in nature, like sigma bond, like pp overlapping bond, head-on overlapping. That means ligands are arranged in a fixed geometry, not randomly. That means these all ligands are arranged in a fixed geometry, not in a randomly. For example, coordination number six, that is octahedral geometry, and coordination number 4, that can be tetrahedral geometry or square planar geometry. So to forming this octahedral geometry, ligands must have to approach through faces. That's why they are directional in nature, the ligands, that is secondary valency. And to form tetrahedral, the ligands must have to approach through corner. That is also directional in nature. So here key points are, in this complex satisfied by two type of valency. One is primary valency, another is secondary valency. Primary valency is ionizable, that breaks into ions, but secondary valency is non-ionizable, that will not break into individual ions. And this geometry depends upon secondary valency. Here the secondary valency inside this sphere, and that is 6, and due to this 6 coordination number, only the geometry is octahedral geometry. So geometry always dependent upon secondary valencies. Okay, now this is explained by this Werner, Alfred Werner. Although Werner's theory was very successful, it had some limitations. It could not explain why complexes have color. So, limitation, it could not explain why complexes have color, why complex have color, why they show magnetic properties, why they show magnetic properties. The exact nature of bonding also he could not explain, the exact nature of bonding. Let me put in charge. This iPad has I think 5% charge. Okay. Now see, he also could not explain the exact nature of bonding. nature of bonding. This all this color of complex magnetic properties, nature of bonding, this all were explained later by the other theories like VVT, CFT, and MOT's theory that we are not going to discuss here.